This is Math 30-1, and we are in Chapter 1, where we have been learning about polynomial functions. And we have reached the final lesson in the chapter. 1.5 looks at applications, so modeling and solving problems with polynomial functions. Now, as we get into problem solving, kind of the challenging part for the most part, will be coming up with an equation and then interpreting the information that we get. When it comes to solving, primarily we will solve by graphing. So that part of things will be a little bit easier. We won't generally be expected to solve algebraically. To begin with, I'd like to look at the getting started questions and check your understanding question from your work text. If you have it, you can look it up there, or you may have it in the handout. Or if you haven't received it yet, well, here is the get started question. So I'd like you to take a few minutes, read through this question, and come up with some answers. So I'd recommend you pause the video at this point and then continue once you've finished this question. Well, hopefully you found this question fairly easy because it's a Math 20-1 question. So here we have a parabola, a quadratic function, where we have vertical distance in meters and horizontal distance in meters. So what's pictured here is the path of a ball when it's kicked. So it gains some vertical height as it moves horizontally, reaches a maximum, and then comes down and hits the ground over there. So in this first question, what's the maximum height of the ball? Well, we look up here and we see, well, what's the highest point that it reaches? And hopefully you saw that is 12 meters. How far did the ball travel when it reached its maximum height? Well, as we look at this point here, we want to see how far horizontally the ball had traveled. And so if I come to there, it looks like, well, it's a little bit more than 8. And I need to look at my scale here. Two grid lines is 4, so one grid line is 2. So that would be 8. This would be 10. Halfway in between here is what we're looking at. So hopefully you had 9 meters for this horizontal distance. Wait, that's the next question. What? How far did the ball travel horizontally when it reached this height? Oh, there we go. 9 is correct. Horizontally, how far did the ball travel? Well, here we're looking at where it hits the ground. Now we're assuming that the ball doesn't bounce after this, so it may have bounced and done some other things, but we want to know after this initial kick, when does it first hit the ground? Here we're at 16. Again, one grid line is 2 units, so hopefully you had 18 meters here as your answer. Well, that was a relatively easy start to this section. Let's step it up a little bit with this construct your understanding question. Again, I'll encourage you to pause the video and restart once you've finished working through this question. Well, here we have regulations for a piece of carry-on luggage with an airline, and we're given information about the length, the width, and the depth. Instead of D, I'm going to use an X as I just think ahead to what's going to be happening in this question. And we're told that it must not exceed. So this must not exceed 100 centimeters lets us think, oh, maybe this is a less than or equal to inequality type question. But as I look down, here we're looking for a maximum possible volume. And so since I'm looking for a maximum here, rather than doing an inequality up here, I'm going to do an equation that will give me the maximum amount. So the sum of these, so if I do a length plus a width plus the depth, the sum must not exceed, but it can reach 100 centimeters. So I'm going to make it an equation rather than an inequality. Next, several models have luggage where the length is 10 centimeters greater than the depth. Well, if I think length and I think depth, which one of these is bigger? Oh, length is bigger, so I need to add that 10 centimeters to the depth in order to get the length. So there I get an expression for the length in terms of depth. Well, now I also want to think, I still have two variables. Well, I have three in total. Let's continue looking here. We want to write a function to represent the volume of this luggage. So as I look at volume, I can think that the volume will be my length times my width times my depth. Well, I want to get to a point where I have a function where my volume is a function of only one variable. So let's imagine it's going to be depth, because I think that is what's going to work. So I want to be able to write volume as a function only of that depth. And so far, I know I can do it replacing this L with an x plus 10. So the W, I don't know how I can replace that yet, but then I do have the x. So I need to come back to this equation up here and say, oh, can I isolate my W? And I can. So I can do 100 minus the length, but instead of length, I'm going to do x plus 10 minus the depth. And then I'll simplify that expression. So I'm kind of running out of space here, so I'm going to come down this direction, and I'll get my width is equal to 100 minus 10. So this 100 here, subtracting the 10, will give me a 90. And then this negative x minus x will give me a minus 2x. So now I can write my equation down here. So for my length, I will have an x plus 10. For the width, I have a 90 minus 2x. And then for my depth, it's just an x. Let me just rewrite this with a lighter colored pen, hopefully. Is this working? There we go. Volume, and I'm going to bring the x to the front, and then I have an x plus 10, and then the 90 minus 2x as my third factor. And we were asked to write a polynomial function to represent the volume. That's what we have. Since that's all we're asked to do, I would stop here. We could expand it, but if I expand this, I'm more likely to make mistakes than if I just leave it as it is. And since we're not asked to expand it, I would just leave it at this point, and where we're asked to graph the function, I would enter it into my calculator just like this. So here's what my graph looks like when I put it on Desmos. It's not especially helpful, and I'm guessing that when you put it in your calculator, initially you see something like this. Now, one thing that you can do on your calculator is you have a zoom button, and you could try a zoom fit. Sometimes that works and gives us a starting point. Sometimes it doesn't. So what I'm going to do is I'm just going to kind of reason through the information that we have. I can see that I have an x-intercept here at 0, and I have another one over here at negative 10. But when I think about my depth, that's what x represents, having a negative depth is kind of useless. So I'm not interested in that one over there, but I'm guessing that there's going to be something further to the right. So I could just keep zooming out, or I could kind of make some smarter guesses. So here I'm going to look for my x max, and I know that the sum of my three dimensions can't exceed 100, so I need some maximum x value here that's going to be less than 100. And I'm thinking, well, since I have three different dimensions, I'm guessing the depth is probably the smallest. So I'm going to say, well, what if I try maybe 50 here as my maximum? And as I do that, I can see, oh, here's my graph here, and I can see it going one direction there, one direction there. Again, from what I know about polynomial functions, if I was to expand it, then I'd have x times negative 2x. My leading coefficient would be negative. It's a degree 3 polynomial. I saw one x-intercept at negative 10, another one here at 0, and another one here at 45-ish. Is it exactly 45? Yeah, looks like it. And so I have my three x-intercepts. My leading coefficient is negative, so this right end is going down. So I want to see there must be a maximum point somewhere in between here. And this graph looks pretty vertical, so it's probably very high up. So I'm going to choose quite a large y maximum value. I'm going to try 1,000 and see what I can see. And already I can see that's not enough. So let's just add another 0 here to make it up to 10,000. Still not there. Let's try 100,000. Well, that's a little extreme, but it got me there. So now I can see there's a maximum value here. So let me shift the graph over this way, and we could zoom out horizontally to see that, oh, there's my cubic function shape, but this is the part that I'll be most interested in over here. Let's have a look again at what the question is asking. To the nearest cubic centimeter, what is the maximum possible volume of the luggage? Well, as we come back here, what do our x and y values represent? Well, the x is the depth of our carry-on piece, and the y is the volume. So since I want to maximize the volume, I want to find this point over here. Well, on Desmos, I can just click on it and it gives it to me fairly quickly. On your calculator, remember you have that second trace button, and you can do second trace to calculate a maximum. You do a left bound, a right bound, and then guess in between to find the coordinates for this point. So here I can see that I'll have a maximum that happens where my depth of the luggage is about 28.6. I think that was in centimeters, and the volume is about 36,210 cubic centimeters. So let's come back here. What is the maximum possible volume? So we can say our maximum volume is about, we said 36,210 cubic centimeters. Yep. What are the dimensions to the nearest tenth of a centimeter? Well, my x, so my depth that we got from that graph, was approximately equal to 28.6 centimeters. And then remember, we had expressions written up on the right, where here we had our length would be x plus 10. So my length is going to be 10 more than this depth, so about 38.6 centimeters. And then the width, well, that's what I had written up here, as you can see, the 90 minus 2x. So here I want to do 90 minus 2 times that 28.6 centimeters. And what do we get when we do that? We get about 147.2 centimeters. So we've answered maximum volume, and then the dimensions, the depth, the length, and the width in order to maximize the volume that we get from that luggage. And that pretty much answers the question. What assumptions did we make? Well, back here when we set up our equation, we did length times width times depth. Well, that would be the volume for a rectangular prism. So we're assuming that the shape of this luggage is a rectangular prism, like a box. It could be cylindrical or something different, but I didn't even think of that. So that was an assumption that we made in answering the question. So that's the type of question we're going to be looking at in this section. So let's look ahead into our notes and look at two examples. First example, we have a piece of cardboard that is 30 centimeters long and 25 centimeters wide. It's used to make a box with no lid. So it's just a piece of cardboard at the moment. We're going to cut out squares, each of side length x centimeters from each corner. So here, the first corner, we can see what the cutout is going to look like. And so we're going to do squares of the same size for each of the other corners. So this is what it'll look like as we make those cuts. And here I just put in that dimension of x, where we can see that the side length, so both going vertically and in this direction, for both of those, the dimension is x because those are squares. Well, when we cut out those corners, our dimensions for the box will change slightly. So because I'm going to fold up this flap that's left over here, that's going to be the height of one side, and this will be another side. I'm going to fold along, there we go. So along this dotted line is where we're going to make a fold to fold up the side. Same thing along here, and along there, and along this third side. So this 30 minus 2x is going to be one of the dimensions. We could say the dimension of the length of our box once we folded up the edges. This will be the width of our box once we folded up the edges. So if we were to sketch a diagram, this is kind of what it would look like, where I have this blue dimension here, the 25 minus 2x. That's this width of the box here for each of those blue edges. This 30 minus 2x, well, that's the length of the box, so that's each of these black edges, and then x is what we folded up, so that's going to be the height of the box. Once we have a diagram like this, it makes our volume equation easier to figure out. It's just a length times width times height. And there's our equation. And we've answered question number 1. Write a polynomial function to represent the box volume in terms of x, where x was the size of this square that was cut out of the corners. Question number 2 asks us to graph the function and state the domain. So just like in that construct understanding question we did at the beginning, there's no need for us to expand this polynomial, and in fact, it's better if we don't. Because if I don't expand it, then I can find the zeros of this polynomial. So imagine that this whole thing was equal to 0. When is it equal to 0? Well, when one of the factors is 0. So it could be when x is equal to 0, or it could be when 25 minus 2x is equal to 0. And the details of rearranging this I'll leave for you, but that'll be when x is 12.5. Or we could have the situation where this 30 minus 2x is equal to 0. And when I solve that, I'll get x is equal to 15. So I have 3 x-intercepts for my graph. If I were to expand it out, I would have an x times a 2x would give me a negative 2x squared, times another 2x would give me a positive 4x cubed. So my leading coefficient will be a 4x cubed, so my right end behavior is going up. It's cubic, so my left end behavior is going down. And I know that I'll have intercepts at 0, at 12.5, and at 15. Well, I could do a fairly rough sketch here, but it's not going to be pretty because I don't draw well on this tablet. So I'm going to remove some of that, and I'll just pull out what this graph will look like as I copied it from Desmos. So as predicted, we do have intercepts here where x is 0, there where x is 12.5, and then here where my x is 15. That's number 2. Oh, except we're asked to state the domain. Let's look at question 3. To the nearest cubic centimeter, what is the maximum volume of the box? So again, here's where you need to make use of your calculator. And with your calculator, we want to find right here, we want maximum volume. So we want to know what's the y coordinate. So for number 3, this is what we're looking at for question 3. what is that y coordinate? So again, you'll do a left bound and a right bound, and you'll guess in between here, and your calculator will give you that maximum value. You did that a fair bit in Math 20-1, so hopefully that's familiar. If not, then you can ask me in person and we can review it. So hopefully you end up with 1,512 cubic centimeters. It says to the nearest cubic centimeter, so this would be a rounded value. Number 4, what size of square should be cut from the corners to create this? Well, for number 4 then, we are looking for what is this x coordinate that corresponds down here. We want to know what this is, and that's what we're looking at for question number 4. So maybe I should put a number sign here. That was for number 3. This is for number 4. When we find that maximum point, we got both those ordered pairs, and hopefully you ended up with about 4.5 centimeters. Finally, to the nearest tenth of a centimeter, what are the dimensions of the maximum volume box? Well, we found the size of the square, so this 4.5, that's one of the dimensions. But again, as we come up here, that's only one. So we also need to do 30 minus 2 times 4.5. So that'll be 30 minus 9, about 21. 25 minus 2 times 4.5, 25 minus 9, about 16. So those are the answers that we're going to state down here as we answer question 5. So we have these two dimensions and the height of the box that we had from question number 4. Let's look at one more example. Clara, or Clara, depending on where you're from, had 3 friends, and they were all born on March 11th. Leslie's 5 years younger, Mike's 2 years younger, Thomas is 3 years older. On March 11th this year, the product of their ages is 61,136 greater than the sum of their ages. Oh, this is one of those questions that's only ever happens in a math class. Well, it's here just to challenge our brains. And really, that's what math is all about. Math is about thinking logically. Math is the study of anything that can be, anything that, it's the study of logic. Anything that can be studied through logic is mathematical. There we go. It took me a minute to come up with that definition again. I didn't invent it. I read it in a book once. What is the book called? Well, it happens to be here on my shelf. Cakes, Custard, and Category Theory by Eugenia Cheng. It was quite an entertaining book. At one point, I was thinking maybe I shouldn't continue teaching. I was between jobs, and my wife got a little bit concerned. So she bought me a math book, and again, I was reminded of why I love math. Anyhow, I digress. Back to the question. Well, we want to know how old each person will be on this birthday. Claire is the one that everyone else is referenced to, so I'm going to say that C will represent Clara's age. Now we have these 3 friends, but we can represent all of their ages in terms of Clara's age. So I can come up with these other 3 expressions that describe Leslie's age, Mike's age, and Tom's age. Well, then we have that statement about the product and the sum. So the product, we're told, is 61,000 something greater than the sum. So product is what we get when we multiply. Is tells me I have an equal sign. And the sum is what I get when I add them together. So there's the start of my equation. It's not a complete equation yet because so far I have the product equal to the sum, but they're not equal. I'll give you a moment to write this down. When I have questions like this, sometimes I get confused, where it says the product is so much greater than the sum. So I start with thinking product, sum, which one of these is bigger? Oh, the product is bigger. So if this left side is bigger, which side do I want to add something to? did I write that as a question here? Yes, I did. Which side needs to be 61,000-ish more to make the two sides equal? Well, hopefully you recognize that since the product is greater, I need to add to the sum size, or the sum side, I should say, 61,136. Now I have an equation. Now this equal sign is true. But that's my process to help me when I get confused with questions like this, and maybe it'll be helpful for you as well. Well, here I've shown that addition for you. So there's no point in having both of those out here. So there's my equation. Let's simplify it down. On the left side, I'm going to keep it in factored form because it's a pain to multiply it out, and I'm likely to make a mistake. On the right side, it's pretty easy to collect the like terms. So that's what I've done to the right side of my equation. Now, how do we solve this? Well, we're going to solve by graphing. So we have a couple options. I could graph the left side as y1 and the right side is y2, and then find the intersection point. Or I could collect everything to one side of the equation to graph and to solve. Well, the recording of this video got interrupted. And so hopefully this is backtracking a little bit and you can put up with a little bit of repetition here. So we've made it to this point where we have the product is 61,136 greater than, so I had to add it to the sum side because the sum was smaller, that much more than the sum. And then cleaning up this equation a little bit, the product, don't bother expanding because we're just likely to make a mistake. The sum side is easy to collect like terms, and so we've done that. And then from here, as we seek to answer this question, we want to know how old each person will be on this birthday. So we want to know the C value that makes this true. What is that C value? Well, that'll be Clara's age. So we have a couple options. I could graph the left side of this equation as y1, the right side of the equation as y2. And then when I graph them, I would look at the intersection point of these two functions. Well, what will that graph look like? Well, let's pull this up here. So here we can see, I'll make this a little bit smaller, and there we go. So I've graphed the left side and the right side. I want to find this intersection point, and that happens in this case for my x value, but the equation that we wrote on the page is a c value when that is equal to 17. So there we have that intersection point. So that's one way for us to solve, and we end up with Clara's age being 17. Leslie's 5 years younger at 12, Mike 2 years younger at 15, and Thomas 3 years older at 20. The other way we could have done this would be to rearrange and collect everything to one side of the equation. Then when we graph the result that we get, we want to look at the zero or the x-intercept for the function. So here we just see a bit of the curve on the right side here. And again, we see that we're getting a c value of 17. So either way we do it. So here we do the second trace to calculate the zero of the function if you have a TI 83 or 84 plus. And for the other one, what we did was a second trace and calculate the intersection point, where we did a first curve, second curve, and guess close to the point. So those are two different ways we could graph and then find our final answer for this question. Final question for this lesson is number 7. The domain of any polynomial function is that x can be any real number. Is this true when a polynomial function is used to model a real-world situation? I'd like you to pause the video here to think about it, come up with an explanation, and then restart the video to see how I would answer this question. You can pause now. Well, here's what I would say. When modeling real-world situations, the domain of a polynomial may not always be x can be any real number. Real-world situations may impose restrictions on what the variable can represent. Often the variable will need to be a positive and may have physical limits on how large it can be. I'll come back to the statement in a moment, but first, let's come back and look at this question here. For this question, when we look at this graph, we see this smooth and continuous curve, but what parts made sense here? Well, I actually didn't finish that question. It said for number 2, graph the function, state its domain. Well, I'm glad that I thought of coming back to this question. As we think about the domain, what's going to happen for these different x values? Well, when x is 0, what's happening? Well, as I look at my box up here, it means that I'm actually not cutting anything out from the side of the box, so my volume is 0. So that's not going to be a useful value. So my x really needs to be greater than 0 for me to have some meaningful and useful box resulting. But then as we look at the graph, we see that once I reach over here at 12.5, again I get a volume of 0. Why is that? Well, as I look up here, from this 25, if I was to come up from the edge to cut out my box that's 12.5 units long, and if I was to do the same thing over here, 12.5 units long, then what I get is basically I've cut everything away from here. And all I'm left with is the little strip of paper in the middle here, which can't even build a box. So that's going to end up being useless as well. So down here, I'm going to have to say that my x value has to be less than 12.5. Now what happens if I go even bigger? Well, if I think of this, if I go bigger, I start cutting away stuff that doesn't actually exist. So even though the graph of this function looks like it's continuous everywhere, for this question, it's really only useful between 0 and 12.5. So just reviewing set builder notation, we could say that our domain, we'll do it this way, our domain is equal to the set of x's such that 0 is less than x, which is less than 12.5, but x can be any real number in this interval. Now, a question that may come up at this point is, how do I know that this can't be 0? Well, if you had put this as your answer for this question on a test or a quiz, I would still give you full marks. Because it's kind of debatable whether we can say we can include 0 or not include 0. If I include 0, it just means I can get a volume of 0. Not really helpful, but neither is if x is 0.001. That's not going to be a useful box either, but it's still part of this domain. And similarly for the other end of this interval. So you could write these as equalities or inequalities for this question, and I would accept that as a reasonable domain. So again, that is why we have this explanation as written here in number 7. The real-world situation imposes restrictions. So we have a limitation on the domain. So measure of success, I can solve problems using polynomial functions. So hopefully you are in good shape to do some practice questions. Here they are listed at the bottom. And with these practice questions, your confidence will grow. All right, enjoy.